Without further ado, I'll turn it over to you, Nancy, and you can tell us a little bit about you before you get started.
Thanks, John. I'm happy to be here and happy to share what I learned about these products with anyone who's interested. The Lifewave products are truly amazing, and my background is my degrees in biomathematics, so I'm a doctor, but not a medical doctor. And I spent my career in medical research and statistics. And so I'm familiar with a lot of things in the biological sciences, but the science behind these patches has really been new to me. Many things that have been learned since I was in college, for sure. And so I have really enjoyed learning about them, and I really am happy to share what I learned with you. So each time I give a talk, I talk about a different patch, and I talk about the science, but the science that I can find that supports the patch, and then I talk about the science that's been done on the patch itself. And so today we are talking about the Alavida Trio, and with that I will share my screen, which takes a little bit of doing right now, because I'm using my husband's computer. My computer is not functioning, so just bear with me a minute. I think I have this figured out now.
We lost it there.
Hang on, no, this is all part of the plan. There we go. Is that it?
That looks good.
All right. Okay. So Alavida Trio, we have 2 lotions and what is called a sleeve of patches. So the little patch here is less than 4 centimeters wide. It's like a little band-aid. You put it on they come in these pouches that are called sleeves. You get 30 to a sleeve. And then we have a day lotion and a night lotion. So I will be talking about the science behind these patches. Now, here we have a before and after picture. And there are many, many pictures on the web. There is a website called myalavida.com, and you can look for more if you like it. But of course, there are many products on the market, and many of them have before and after pictures. So it's really hard to sort out what is going on and what's good for you and what's not good for you by looking at the before and after pictures. I think truly this looks remarkable, but let's go a little deeper. So in the middle, we have the CEO and founder of Lifewave, David Schmidt. And he developed these patches to they're crystals, and they reflect the light that comes off of your body. They're designed to reflect specific frequencies of light, and those frequencies are chosen to do specific things. And he told us in this talk in 1921 that the aim of the light from the Alavida patch is to increase this peptide called, well, it's got 2 names, epithalon. And I'll say a little more about that. I'll say quite a bit more about that. So just to talk about, just to show this picture to sort of remind you how a crystal can affect light. We have here light coming in from behind a crystal, and it's being separated into all these different frequencies. And so in the case of the patch, the light comes off your body and gets reflected back, and not all the frequencies get reflected back, just the ones that are going to do what was intended to do. And a lot of the early research was done by Thomas and Helen Brzezinski. Thomas was a PhD on the faculty at the University of Washington in biophysics, I believe it was. Helen was a PhD psychologist, and then Piven et al. This was work on the basic operation of the patch, proving that it handled the light and did what Lifewave was claiming it did. So those are good articles. Most of the research that I will cite can be found on the Lifewave website. If you scroll all the way to the bottom of the front page, there's a menu, and one of them is research and science, and they have a lot of articles there. So this peptide that's being targeted by the Alavida patch is made in the pineal gland. So it's this little purple dot in the middle of the brain, and very deep in the brain, very protected, and a very important gland for the functioning of our well-being. So Dr. Vladimir Anisimov is on the left here, and he's the one that discovered this peptide, actually discovered that it existed. And then Dr. Vladimir Kavinson isolated it from cattle and is actually made, so he will sell you, he will give you injections of this peptide. So one might say, why do I need Lifewave? Well, you can't take it as a pill. And because one that will work in your body doesn't exist. And if you want to go to St. Petersburg and get injections, then you're welcome. We are fortunate here with respect to this talk. Dr. Kavinson has done quite a bit of research on this peptide. So we have more information than we have on some of the others. And we'll be seeing more about him as we go along. So when Lifewave makes a patch to target a particular peptide, they target really basic peptides that have a lot of effects. And then when they've done that, they have to decide how they're going to market it. And so the Alavida patch is marketed for skincare, but we're going to see that it has a wide-ranging effects. But we will begin and focus on skin because, that's where the company has chosen to focus. So this epithalon that is the production's enhanced. The epithalon production is enhanced, and this is a very short molecule, and it can penetrate the cell membrane. Once it gets inside the nucleus, it promotes the production of collagen by activating skin fibroblasts. And I'm going to show you pictures of that so that you understand more about what I'm talking about. So when I'm talking and you hear things you don't recognize, just let it wash over you so that you sort of recognize the term. And then I try to explain, I really try to explain everything in detail so there's no big secrets. And if I don't do that, then you can ask questions at the end or be in touch with me. So there's a study in 2014 that says epithalon causes fibroblast numbers to increase by 30 to 45%. And again, it impacts skin aging by activating the repair and maintenance of the extracellular matrix. I'll tell you what that is, and that makes our skin strong. So this is a picture of skin, and we have the male version and the female version. This is the epithelial tissue. At the top, we have several layers. The top is called the epidermis, in the middle is the dermis, and then we have the hypodermis, and then underneath it is the muscle. And you can, you all think of your skin probably largely as protecting your body. It protects your organs and your blood vessels, and it protects your muscles. So here's a list of the things that it actually optimizes. It's a very busy piece of tissue. It optimizes secretion, what's going out, what's being secreted. It optimizes absorption. It optimizes excretion. It optimizes filtration, letting some things in and some things not, diffusion, and sensory reception. And when I first gave this talk, I looked all these things up in the dictionary because I decided it wasn't quite so clear, what was the difference between secretion and excretion. And if you're interested, I encourage you to come back to the slides and do that. Just checking them out in the dictionary. So if you look at these pictures, well, what's the difference between the male and the female? There's these little white hashes, which are collagen bonds. And in the male, they're crisscrossed, and in the female, they go straight up and down. And these are structural support pieces to your whole skin setup. So I'm going to show you a few pictures here in succession to get an idea. So sort of zeroing in more on the dermis, you see you have the hair follicle. It's very busy. You have the hair follicle, you have veins and arteries, you have sweat glands, you have all kinds of things going on. And then we look now on what's the difference between skin that's rich in collagen and skin that's doesn't have enough collagen. And so on the left, again, it looks kind of like a little, cake treat that you might get at the pastry store. Just everything's nice and plump, looks tidy. And then if you don't have enough collagen, you can see these little crosshatches. They're broken apart, and where it was broken, the skin begins to sag and dip, and you have some cells that are just sort of either totally squashed or missing that are in the middle. So when you don't have the collagen, everything is getting squeezed together and can't function as it should. So now here, this compares a younger skin with an older skin. So the first thing you notice is the top of the skin for the younger person is nice and tight, and for the older person is deeply wrinkled. But if you look at what's going on underneath, again, you have the collagen fibers for the younger skin are holding the whole apparatus up, like the 2x4s, studs that are holding up a house. And in the older skin, you can see they're all broken and falling apart. The other two things in here, we'll talk about the fibroblasts, because the collagen stimulates the production of the fibroblasts as well as other things. And then there's these tentacles, which are called elastin, and they're what's make your skin spongy and so it's nice and soft. We won't talk much about elastin in this talk, but we have here that collagen is this framework that holds everything together, and as such, it plays a large role in the cell movement inside the dermis, the shape. Okay, this is just a little bit of a switch. So here we're talking about the skin, but every cell has collagen in it. And so each cell in your body, the collagen makes up the framework, the structure that, I think I have another slide on this too, you'll see. I'm going to wait, hold this spot. Couple slides down. Here's a picture of young skin and old skin, and here we have the histology, which is actually what you see under a slide, under a microscope. On the left, we have for the young skin, and on the right, we have the older skin, and you can see how it's all disintegrated. And again, you can see the breakup of the collagen fibers and the disappearance of many of the fibroblasts. So let's just define a couple of things. So fibroblasts themselves, we already mentioned that they synthesize collagen, which is the main structural component of the extracellular matrix we were looking at, found in various connective tissues. The extracellular matrix is this three-dimensional network we were kind of looking at that's outside the cell, that has micromolecules and minerals, and it provides the structural support to the cells that surround it, the surrounding cells. So this is the picture I was going to show you of a cell itself. So here we have a cell, we have the mitochondria, we have the nucleus, and we have all kinds of things going on inside the cell, but this green stuff is the collagen. So it's this structure that's actually holding the cell apart. So, so it doesn't collapse on itself, just the way your skin might. And collagen is important. In fact, collagen is the most abundant protein in the body. That's 20 to 35% of your body's protein is collagen. It's 90% of our connective tissue and 90% of your bone matrix. So it's the bulk of your connective tissue that's associated with water, with bound water and ions, listen to this, to produce a hydrated state. Now I'm going to show you more about what that means, because everybody's talking about hydration now and you should drink water. And so why should you drink water? I mean, it's really cool. I found some pictures that I think make it pretty clear why hydration is really important to this, well, to our skin, but to everything that is collagen related. So here we go. First, we're going to just take a detour and look at how collagen depletes with age. So if we start out when you're young, let's say 100% of the collagen, if you call what a youth has 100%, and you go out over time, here where it's age 60, you only have 40% of your collagen left. And by 80, you have 20% of your collagen left. And you start to lose those fibroblasts that produce collagen about age 25. And of course, it accelerates if you don't take care of yourself, like if you smoke, you get too much sun, pollution, and a poor diet. So we really want more fibroblasts producing more collagen. This is what collagen looks like. So we start on the left with an amino acid, and just think of that as a collection of molecules. They have particular characteristics that are important for life. But if you have this string, I think there are like 32 different amino acids. You'd recognize a number of the names. But for collagen, the ones that make up collagen, collagen is twisted, 3 of them twisted together, much like DNA. I don't know, the body must like twists of 3. So you get 3 of these strands and you wrap them together, and then you have a collagen molecule. And on the next slide, we'll have it called a collagen peptide. So I just tell you here that peptides are short chains of amino acids that are linked by particular kind of way, which is called a peptide bond. So we still have to make up the structure. And so now think of weaving a basket, and you've got reeds. And so you take the reeds and you wrap 3 of them together, and then you start binding all of those strands of 3 into thicker strands, and pretty soon you have a basket. And in this case, you have a collagen fiber. So now this is the exciting part for me, because I didn't understand it. this is where hydration comes in. So look on the left first. You have, on the top here, you have some colored molecules up here on the top. And at the bottom of the picture, you have some more colored molecules. Those are 2 strands of collagen. And then between them, you have these white little molecules that are connected, and they call it a bridge. There's a bridge between the 2 collagen molecules. And I'll be darned if that bridge isn't made of water. So water is holding your collagen together. It's actually, we think of water as fluid, and how in the world is it going to really, do something other than help, maybe it's in our blood, washing away the garbage or help carrying the red blood cells. But this is showing you that it's part of a fundamental part of the structure that holds us together and upright. And in the picture below, you have 2 more strands of collagen, and then you have another set of water molecules that span between the 2. And you can see they're different. There's different shapes. This is like a pentagon here, and here you have a pentagon, but there's other things connecting them. And so there's a whole batch of these collagen bridges that where you have different shapes of the water molecules holding the collagen together, and they all have different names. And so what I show you here is, have a bunch of collagen molecules that they're kind of stretched out so you can see them. And then they show how the water molecules traverse between them, and they get all wrapped up to get you the pictures on the left and at the bottom. So this gives me a whole different appreciation for the significance of hydration. This is another picture, which I don't want to go into too much detail on the chemistry, but if you just look inside this little circle, a water is 2 hydrogens and an oxygen. So here's a water molecule right here, and it happens to be linked to a hydrogen with a positive charge. And this just shows how a bunch of them get connected together. But what I want to talk about is the fact that this hydrogen moving around can cause some of these to connect together, but other things can get stuck in there. And on the right, we have the little strands representing the collagen molecules. And we also have a sulfide too, disulfide too. So we have up here, we have a sulfide with a hydrogen pairs that get connected together. And here we just have the disulfide pairs that get connected together. And it's been shown that those are much stronger than just having the hydrogen and the water connect them together by themselves. So hold that thought, because I'm not so interested in the sulfide. I'm interested in silica, and I'll tell you why in a couple of minutes. So first, here we have a really pretty picture of the collagen, just to give you something to look at. If you don't want to read the words, you can listen to me talk. So back in 1998, Dr. Ho did some scientific work that caused him to conclude that the combination of collagen and water creates an electrically conductive continuum that extends throughout the body and even into the interior of cells. So this means not only is that collagen structure holding you up and giving you structure, but it's also a communication system. You've got electricity going we think of information getting passed through our body by our nerve cells, our spinal cord, and certainly that happens in a big way. But what we, I think, have probably paid too little attention to is the communication that is spread, in the case of the skin, just spread along the surface of your body. And as we've seen, the surface of cells, and if we see a little bit later, other places where collagen is. So collagen, here we have a report from 1976, so that's going back a ways, that collagen has both piezoelectric and pyroelectric properties. I'm going to show you a picture of that. You might imagine pyro is like fire, right? Pyro. Maybe you don't know piezo, but if you've been camping recently and you get a stove and it starts without you're having to use a match, it's called a piezo spark. So I'll explain those two things. You've got these two kinds of electricity running through your collagen. The papers about the Lifewave products that have documented that the patches will increase the electrical conductivity around the acupuncture points and regions around it, which is one of the ways that the patches communicate to your body to do what they were designed to do. So all of this supports that activity. So here's my pictures on pyro and piezoelectricity. On the left, we have changes in temperature get converted to electrical current. You have a little candle, you got a battery, and it can light your light bulb. And with piezoelectricity, this was the one I focused on. I've used this slide to describe communication between the crystal that's in the Lifewave patch and the body. And now we're focusing on it, describing the communication across the collagen in the body. And what's that got to do with crystals? Well, that's where we're going to come back and tie the silica into that hydrated collagen matrix. So bear with me. This refers to crystals. And if you look at this picture, you have negative and positive charges on one side of the crystal and negative and positive charges on the other side of the crystal. And there's no force applied, so there's no current. It's just sitting there. But if you apply force, you squeeze this thing, you actually push it, then the negative charges get lined up on one side, the positive charges get lined up on the other, and you have electrical current. So, I mean, that's pretty cool when you think of it in your body. So here is my connection with silicon and the collagen. So silicon is a very, what I think it's like the third most common molecule in the world. It's a type of quartz, which is a crystal. And as such, it has the crystal's electric and vibrational properties. And because it's like everywhere, it is in natural water. You're drinking it all the time. You're getting lots of silicon. So that was reported back in 1986. So if the water you're drinking has got all the silicon in it, and the silicon acts like the quartz, and the molecules get caught up in that collagen, hydrated collagen network, then you have all of your skin tissue, all of your epithelial structure is operating like a crystal. And that permits it, with its water bridges, to convey information, electricity, and vibrate throughout the body. So I think that's pretty cool. And having sort of come to that realization, I rediscovered, because I had seen these before, but the impact didn't quite dawn on me. These papers by Becker and Sheldon in 1990 and 1985, where they concluded what's here in the middle, that the larger bioelectrical system of your body is composed of proteins such as collagen, which utilize their electrically conducting properties to move energy from one location to another. So voila, we have the fundamental setup for how the Lifewave product communicates its instructions to the body. We have how those instructions get traversed and communicated through the body. And we have other properties that are relevant to other patches that we will talk about now and then. Now, one of the things I said is that the collagen that's being stimulated by the patches, the Alavida patch, the collagen production, is a big component of the epithelial, but the epithelial layer is not just in your skin. And so to sort of emphasize that with a slide here, I've got this picture of the inside of a blood vessel. So here's the inside of a blood vessel. Here's this little arrow says shear stress. So what it's denoting is the fact that you've got your red blood cells just catapulting down that blood vessel. They're going fast and they're hitting the walls. And then down here, this is the wall of the blood vessel. And so it's got the epithelial cells, and you want those nice and strong and plump, and you want them to do what they're supposed to do. And to give you an idea of, at least a partial idea of what matters here, you have the structure, which I like to think of as kind of like if you're in a salt bed in the edge of the sea, you've got, a lot of seaweed and stuff. And what you have, these little yellow dots are sodium molecules. So they're going flying by and they get caught in this network. And then they filter down to the epithelial cells. And it's up to this layer of tissue to decide. You see there's a separation between the different cells. And if that separation is big enough, the sodium is going to get through. And if it's too tight, it's not going to get through. And so the epithelial tissues are regulating whether the sodium's on the inside or the outside of the blood vessel. And the sodium salt, you want it to be where it's supposed to be. And so if this network of tissue that catches the sodium gets torn off by the blood vessels running through, then all that sodium just gets rushing down the blood vessel, and I guess it gets stuck somewhere, but it certainly has no opportunity to go through here. And your balance, your pH balance gets messed up. So you want this whole system to be healthy, and to have it healthy, you need healthy epithelial cells. So now we're going to go through just quickly a few slides that talk about things that the molecule, the peptide epithalon, does besides just be in the epithelial cell, which was certainly plenty. But I said what's on this slide earlier, I'm just going to repeat it. It's a very short molecule that can penetrate the cell membrane without the aid of other molecules that we call transporters, helping it along, makes its way to the cell nucleus directly. And once there, it can affect the regulation of genes, activate some, turn some on, turn some off, and make big changes. So you want that working well. Now I'm showing Dr. Cavason's picture here because he did this research that I'm showing you on the next few slides where his picture is. So epithalon, oh, and the reason there's kind of two names is one's the real peptide name and one's the name of the synthesized product that he makes, but the mixture, the literature's got them all mixed up. Like it's hard to separate the two. Like they sort of think that the only one that's around is the one he made and not the real one. So I didn't get those separated out. I just called them one thing or the other. Anyway, and then of course he's in Russia. So when there's a translation, things get translated different ways because you have to go from the Cyrillic to the Latin alphabet. Anyway, epithalon, our peptide, helps regulate melatonin synthesis. And that's really important for maintaining our circadian rhythm so that we sleep when we're supposed to sleep and stay awake when we're supposed to stay awake. And if you look at the picture on the right, first, this is in monkeys. We have melatonin levels on the left. And on the left, the two bars on the left are monkeys that are young monkeys. They're 6 to 8 years old. And so the blue is the placebo and the red has the red monkey's got the epithalon. And so if you have a young monkey, it didn't matter whether you got the peptide or not. But for monkeys that were 20 to 26, you see that if you were the control monkey, you have a lot less epithalon than you did for the younger monkey. But if you got your epithalon injections, then your melatonin levels are much higher than they even were for the younger monkeys. And not only does he have this data, but he also has a study in elderly people. And so people that are 20 to 40 years old, I'll just read the means here so we can focus on it. The melatonin levels in the units that he's measuring, for the healthy people, you get a 63. And then he takes the older folks, 60 to 74, and I don't know, I'm 75, so I kind of guess I missed the cutoff, but he's got two groups of those, one that just got vitamins and another that got so that's the control group, and the other that got the epithalon from the pineal gland of a cow. And the control patients, initially and after they got their vitamins, are still a long ways from the young folks. So here you've got a 32 and a 28, long ways from 63. The little stars mean statistically significant. For the patients that got the treatment, when they came in, their mean value of melatonin was 24. So they were worse than the young people, and worse than, on the average, worse than the control patients. But if they got the after they got the treatment, they're up to a 59 mean, which is really not significantly different from the young people. So it made a big difference, and it's demonstrated that way. Epithalon also affects the immune system. It promotes something called an interferon gamma, which is, if you get the flu and you feel and you got that hot flash, that's interferon. That's kind of making you feel sick, but it's your body rising to the occasion to fight the infection. And it does that by boosting what's called T cells and helps your overall immunity and well-being. It also normalizes the endocrine system. So this is a system of glands that are located throughout your body. They produce and secrete hormones into the bloodstream or into the fluid that surrounds the cells. And also the endocrine system includes receptors in various organs and tissues that recognize and respond to the hormones. So we could probably do a whole talk on these things that I'm skipping by quickly, but we don't have all night. So, wow, my goodness. And let's not forget cancer. Here is a study in rats, and we have 2 rows here. The rats are given cancer. So one is, there's 2 different ways they're given cancer, one by a drug and the other by radiation. And so the control rats are here. For the drug, 81 of them got, I don't have the total, and 81 got cancer, and then the others 16, and the issue is the different, these are percents, 81% got cancer, and for the radiation, 16% got cancer, but if they were given the peptide, the 81% was instead 26%, and the 16% was 3%. So not yet available for human treatments, but very intriguing. And now I'm going to take a few slides to talk about epithalon and longevity. Because before I can talk about epithalon and longevity, I have to talk a little bit about what's known or thought to be known about longevity. So here we go. Take a breath. This up here is Leonard Hayflick, and he came up with the model, which is called programmed cell death. So he observed that if you put cells into a culture and you grow them, what we have here on the y-axis is the number of times that the accumulated number of times that the population of cells doubles, how many times it replicates. And on the x-axis, we have how long they're in culture. So what you see is when you first put the cells in the culture, they're kind of quiet. There's not many doublings going on. And then they start to double, they double. And then they sort of stop doubling until they're not doubling anymore. They're just sitting there dead. And this particular finding refuted the current theory by a French Nobel laureate who had argued that normal cells were all immortal. So this is called Hayflick's limit after the Dr. Hayflick, who observed it and described it. Now, it in this observation can be interpreted in terms of the chromosomes. So here we have 2 chromosomes, and these little caps at the end are called telomeres. So those are the little gray pieces. And you start out, you have a nice cell that's got 2 nice chromosomes that are nice, and their telomere, the chromosomes are nicely capped with the telomeres. So you start out with 1 cell and it divides. And you see down here that telomere got a little shorter, and it divides again. And the telomere gets a little shorter. And David Schmidt talks about this all the time, telomere shortening, or he has in a number of talks. And then it doubles again, shorter, and it keeps doubling until you have no telomere left. And this is when the cell is essentially dead. It's quits dividing. So those that are interested in longevity, scientists that are interested in longevity, some of them are really focused on how to keep these telomeres from shortening like they do. So what does epithalon have to do with telomere length? Well, we're back to studies that were done by Dr. Cavinson. And what we have, well, the conclusion's really here at the bottom. This is the important thing. Goes with the pictures. So red for red and blue for blue. So the conclusion for fibroblasts, divisions, the number of times they're going to divide human divisions in a culture, but it's a good sign. The number of human fibroblast divisions increased by 42.5%. So it's from the control to the ones treated with the peptide. And the average length of the telomere increased almost 2.5-fold. So that's in blue. So epithelon prolonged the vital cycle of normal human cells, overcoming the Hayflick limit. Oh, what I wanted to show you when I was looking at the divisions of the cells in that first slide, the point at which the curve goes flat. In humans, that corresponds to about 120 years. And right now, that's pretty much where we see the limits of, with some rare exceptions, the limits of human life. We have the number of people between 100 and 120 getting increasingly more dense, but we don't have, we haven't started pushing beyond that 120 limit with any, except in the rarest of cases. So here is the study on longevity. So now we're actually looking at people, survival of elderly people. So bless his heart. Look, he starts here in 1982 with a group of people. And he says, okay, those people are all alive. And then you got the age of the patients over here. Both groups, treated and untreated, were approximately 65 years old, plus or minus a year. So 64 to 66. And you have the patients and on the y-axis here, you have the survival rate. So the years go by 92, and he follows these patients, 92 to 2007. By 2007, if you did not get this peptide, only 40% of those patients are still alive. Where if you did get this peptide, 70% of the patients are still alive. So that's a remarkable difference, because obviously there are lots of things that can cause you, I mean, you know, accidents. There are lots of things that can cause you to die besides your general well-being, particularly your epithelial cells. Anyway, a study in humans. This is a longevity study in humans. It's quite nice to have. Okay, now I'm going to talk quickly about the Lifewave products themselves. First, there is a website, myalavida.com, and you can go there for details. The lotions, just a quick few word about the lotions. They're described well on this website. So this is actually a picture taken from the website. It's got this list of titles, and you click on it, and then this larger description comes up. So one thing that is true, that's wonderful, is that they're full of oils, but they're not greasy. And one of the reasons they're not greasy is that David Schmidt recruited a former Estee Lauder chemist to design the lotions for him, and he gave them part of the specs. Is a morning lotion that the day lotion that, you know, is aimed at protecting you from radiation and sun damage, and there's the night skin that's trying to firm your skin, and both of them are trying to work on your wrinkles, but as well as your general health. But one of his specs was that they should be as the ingredients should be as close to the composition of your healthy skin tissue as possible. So I will leave it to you to run through the rest of these ingredients, and there's some intriguing, let me go through. There are some special things that are noted like this. You can read each one, that are in terms of the antioxidants that are in this the lotions are absorbed, have antioxidants that are absorbed 50 times more better than regular vitamin C. And so if you scan through here, you're going to find little gems that are wonderful like that. And David always likes to note that what's important is what they don't include, which is all the bad stuff listed here. And moving along, I will give you quickly the results of I think there's like 3 studies that have been done on the Alavida patches. So this BioScreen Testing Services did a batch of studies and came to the conclusion that the lotions increased skin hydration, improved skin firmness, improved the appearance and evenness of skin tone, reduced the appearance of fine lines and wrinkles. The last 2 here are based on a survey results, and improved the overall appearance of your health. So that was one study. This is a study that uses a machine called an electrointerstitial scan machine, which I always like to describe a little bit because it's like an EKG, but it works at a much lower frequency. So somebody puts their hands on some metal plates, and then there's electrodes throughout the body, and the conductance, electrical conductance through the body is measured, and by that they can describe the electrical conductance around different organs. And so this picture on the right shows you how the readings work. First is they have a DC current, so it doesn't penetrate the skin. And so you see here the red current goes blasting through the cells, and that's most modern medicine doesn't pick up anything because it's too strong. And this picks up the current that's surrounding the cells, and that means it can tell you whether there's resistance and whether the cells can actually get the nutrition and the communications that they need. Because, for example, if you don't have enough oxygen, you can see these cells are all swollen up and the electrical current can't go through at all. And so this device measures this. And in this study, it was a 2015 pilot study. I'm looking here. Homer Nazarin was a PA on the faculty of the University of Texas at El Paso, bioengineering here, and he's retired since. At any rate, they had 10 subjects. They measured 20 organs. Everyone was their own control. They patched nightly for 5 consecutive nights a week with 2 nights off for 30 days. And here you have all the organs that they evaluated, and everything in green was significantly improved by the Alavida patch. So the only thing they looked at that wasn't were the intestines, and who knows, if you used it for 3 months, then maybe the intestines would show improvement as well. And I think this is my last slide. David Schmidt describes a drop in oxidative stress in his talk about the Alavida patch. On the left, we have this machine that's called a biopulsar, and I'm pretty sure that David has since then purchased one of these for his own laboratory. You sort of get case studies because they do these pictures, but it's still interesting to see what's being shown. So we have 2 before and after pictures. On the left, you see a lot more dark blue. On the right, you see a lot of turquoise. So turquoise is good, and the dark blue represents oxidative stress. So when I talk about oxidative stress, I like to tell you just a little bit about what it is, because everybody talks about oxidative problems with free radicals, which cause oxidative stress, and I don't very often see an explanation as to what those really are. So first, free radicals. Think of your engine, your car engine. You've pulled up the hood, you took one of the leads off of the battery and you just sort of threw it there, and then you went out and drove the car, so that one of those leads is banging around inside, and anytime it hits anything metal, you've got sparks going off. That's what your molecules that are turned into free radicals do. They've had your electrons here are supposed to be paired. You've got two, well, paired means then they're canceled each other out in terms of charges. But if you just have one here without a pair, then it's careening through your body, pulling it, trying to pull electron. It wants to be paired. It's pulling electrons off of other molecules in your body that maybe should have their electrons attached, and you really don't. Well, so I can't say you really don't want free radicals, because they're part of your natural respiration and protection of energy. They're just part of the garbage system. So you produce them naturally, but you got to get rid of them. And what this shows, the green thing is an antioxidant. It's basically a molecule that's going around and giving away electrons to these free radicals to take the cable that you had in your car and put it back on your battery and calm it down. So that's free radicals. And the result of having too many free radicals, you see the little teeter-totter. So if you don't have enough antioxidants and you got too many free radicals, then you get you don't have the right electron balance, and that leads to tissue injury and inflammation. So this machine can measure the energy that describes this process, which is pretty cool. So Lifewave products are wellness products. There is no statement by me or anyone in Lifewave about how they are going to cure diseases. They are wellness products, and if you have a serious disease, you should be talking to your doctor about them. And with that, I will just say that that there's a lovely group of patches. You can catch other talks about these patches on my YouTube channel at Nancy Flournoy. And with that, I will encourage you to be happy if you come back and join me on another Friday, first and third Friday, this time, this place. And when I'm not here, John Bishop is going to be talking the first and fourth Fridays and Saturdays with a link that he will be sending out. It's here, johnbishop.beconnected.com, although maybe he'll go back to Zoom now that he's at the United States. So I'm sure he'll be sending out information for next week. So I hope I've entertained you a little. I hope I've told you a bit, and I thank you for coming. I will stop sharing my screen and be happy to take it's so light. Maybe we should do questions on the side. So why don't I just stop the recording, and then